Okay, so this is review problem 6C. You're given this function h, defined by the formula. I write it as x, she wrote it as n, x squared over x squared plus 1, and I wrote it as x because its domain is the interval 0 to infinity, and its range is the interval 0 to infinity, implying the positive real numbers. And we're kind of used to using x for the variables there. So this is a subtle problem only because the numerator and denominator are so close to each other, and you kind of don't really know exactly what this behavior is going to be. And the simplest way to get to it in a case like this is using calculus. What I'm going to do is calculate the derivative of h. H prime of x. Derivative of h is, well, remember the formula for the derivative of the quotient is f prime, fg prime minus, I'm sorry, let's see, it's f prime g minus fg prime over g squared, where f and g are the numerator and denominator respectively. So that derivative is going to be the derivative of x squared, which is 2x, times g, which is x squared plus 1, minus the top, x squared, times the derivative of the bottom, which is 2x, divided by the bottom squared. So calculating away here, I have a 2x times x squared, which gives me a 2x cubed, and I have a minus x squared times 2x, which is a minus x cubed. Those cancel each other out and leave me with the term 2x times 1 upstairs. And downstairs, this denominator, x squared plus 1 squared. Now, remember, we're assuming x is a positive real number. The denominator, no matter what you plug in for x, is a positive number. So it's x squared, which is non-negative, added 1 to it, which is positive, squared again is still positive. So the denominator is a positive number. The numerator is greater than 0 as long as x is greater than 0. So this is greater than 0 for all x in the domain and what does calculus tell us? That if the derivative is positive throughout the domain, then the function is monotonically increasing throughout the domain. So therefore, by calculus, h is monotonically increasing throughout its domain. An interesting question would be to consider what happens when x is 0 and negative, but that's not in the problem. So, I guess you've studied the fact that a monotonically increasing function is 1 to 1. I think that was the problem, therefore, so this is therefore 1 to 1. The question is, what does that graph look like? You may be asked, what is the range of this function? So you might want to look at the graph, and the way the graph looks is this. Here is the real axis. So this is the 0 line, this is the number 1, here's the number 1. I'm going to put a dashed line at y equals 0 right there as well. Notice that when x if I take x near 0, this denominator goes to near 1, the numerator goes to 0, so as x approaches 0, this dives into 0. So it's approaching 0. When x equals 1, this is 1 over 2, so it goes through this point at the half here. So this is somehow going through that. And finally, if we look at our trick of multiplying the numerator and denominator by the power 1 over x squared, you can notice that h of x equals 1 over 1 plus 1 over x squared, which is a way of writing it to let you understand what happens as x gets large. When x gets large, this term is going to 0, and these are, of course, constant. So it's approaching 1 slowly from below as we go to infinity. So this curve keeps on going like this, asymptotically, never reaching 1, but never ceasing to approach 1 as you get towards infinity. So this is a schematic, at least, graph of this function. We have to take a second derivative and kind of see what the behavior is as it approaches 0 and what happens negatively. So this is somewhat schematic picture right here. It does go to 0, but whether it goes in like that or comes in with a little smooth bottom out and keeps going around the other way, it's not clear without doing some more analysis, which I'm not going to get into. But that's the picture.